What's up, everybody? Welcome to the 9th lecture of trig. Today we're going to be talking about section 2.1, which is really just about using your fundamental trig identities. Having said that, before we get into a bunch of examples, I want to direct your attention to the PowerPoints or PDFs, whichever you're using. I think it is the first slide once you get into section 2.1. I provide y'all with a convenient table. It's really just all of your trig identities that you're going to want and that you're going to be using for this particular section. And throughout the rest of the PowerPoints and throughout the rest of the slides, I provide y'all with other tables akin to the one that's in 2.1. So if you haven't looked at the PowerPoints, the PDFs, whichever format you prefer, start doing that because there's going to be a lot of useful information there. Also, there are a lot of worked out examples that I gave in those slides that I'm just not going to be able to get to in these lecture videos. So if you want to see more examples, also look there as well. Having said that, let's jump into it, and let's start by trying to solve this problem. So we want to find all 6 trig functions provided the secant of our angle is equal to -3/2 and the tangent of theta is greater than 0. All right, so how are we going to go about this? Well, looking at it, we get a freebie, right? We know that secant of theta is equal to 1 over cosine of theta. So cosine of theta is equal to 1 over secant of theta, which is going to be 1 over -3 divided by 2, or -2 over 3. So already we found cosine. Cosine is equal to -2 over 3. Let's write that up in the corner up here. Cosine of theta is equal to -2 over 3. All right, so now we need to find sine, cosecant, tangent, and cotangent. How are we going to do that? Well, we can start by using the Pythagorean theorem, right? Or, the Pythagorean identity, which states that 1 is equal to sine squared plus cosine squared. Well, we know cosine squared, and we're trying to solve for sine. So, if we subtract cosine squared from both sides, we can solve for sine squared. 1 minus cosine squared of theta is equal to sine squared of theta. Well, we know cosine is -2 over 3. So squaring that, we're going to find that 1 minus cosine squared is actually 1 minus 2 over 3 squared, -2 over 3, which is equal to 1 minus squaring the -2 is going to be 4, squaring the 3 is going to be 9. So we get that 1 minus cosine squared of theta is equal to 1 minus 4 over 9, which is equal to 5 over 9. So we know now that sine squared is equal to 5 over 9. So sine is going to be equal to plus or minus the square root of that. So how do we know which one to choose? How do we know if we should choose plus or if we should choose minus? Well, there's two different ways we can go about this. We can start by saying, yeah, this tangent's greater than 0. That only happens in 2 quadrants. So, let's actually draw that over here. So that only happens in 2 quadrants. In this top right quadrant and in this bottom left quadrant. That's when tangent theta is greater than 0. Well, looking at this, because cosine is analogous to x, the x position along our unit circle, along the edge of our unit circle. And we know that cosine is negative here. We know we must be somewhere over here, right? In this bottom left quadrant. Well, looking at that, that means sine has to be negative. So we can come over here and say, cool. This means sine theta is equal to the negative of the square root of 5 over the square root of 9, which is equal to the negative of the square root of 5 over 3. So that's one way to go about it. The other way to go about it is to say, all right, well, I know tangent is equal to sine over cosine. And I know cosine's negative, but tangent is positive. Well, it must be then that sine is negative. That's the other way to go about this. All right, so we now know sine theta is equal to the negative of 5, or the square root of 5, over 3. So let's go ahead and find cosecant now. Since we know cosecant of theta is equal to 1 over sine theta, we know the cosecant of theta is equal to 1 over negative square root of 5 divided by 3, which is equal to negative 3 over the square root of 5. So this is a cosecant. Is equal to negative 3 over the square root of 5. Okay, what about tangent? Well, tangent's going to be sine over cosine. All right, that's straightforward. Tangent of theta is equal to sine theta over cosine theta, which is equal to negative square root of 5 divided by 3 over negative 2 over 3. Well, we know that this is like taking negative square root of 5 over 3 and multiplying by the reciprocal of negative 2 over 3. The 3's are going to cancel. The negatives are going to cancel. And we're going to be left with the square root of 5 over 2, which is a good thing because we were told the tangent is positive. And what we just got was a positive tangent. Everything's looking good so far. So tangent of theta is equal to square root of 5 over 2. And the cotangent is 1 over tangent. So same trick as what we played before. Cotangent of theta is equal to 1 over tangent of theta is equal to 2 over square root of 5. And we were already given what the secant was, so we have all 6 trig values. Okay. So in this next example, we just want to simplify this expression. Well, looking at it right away, there's nothing that jumps out, right? Like nothing's obvious here. But if I think back to algebra, we might recall that we can pull out sine x, right? Okay. So we pull out sine x. When we do that, we're going to end up with cosine squared x minus 1, that quantity, times sine x. Now we might recall Pythagorean identity yet again. What it stated was 1 is equal to cosine squared of theta plus sine squared of theta. What we've got is cosine squared minus 1. So it's going to take some rearranging up here. To start off with, we can subtract 1 from both sides. When we do that, we're going to end up with cosine squared of theta plus sine squared of theta minus 1, all of that's equal to 0, right? Okay, so it's starting to look a little bit closer to what we wanted. Because we can rearrange these terms. And we're going to end up with cosine squared of theta minus 1 plus sine squared of theta. Okay, so definitely looks promising now, right? Because we've got this, and this is what we want to know. Well, why don't we just subtract sine squared from both sides now? Since everything's equal to 0, subtracting sine squared from both sides is going to give us negative sine squared of theta is equal to cosine squared of theta minus 1. Which is exactly what we're trying to solve for. So, we can go ahead and just plug in negative sine squared here. When we do, we're going to find that we have sine squared, my mistake, sine x times negative sine squared of x. Well, we can multiply by that sign now and simplify it down to negative sine cubed of x. And that's it. That's all there is to it. So let's look at another problem. So for this example, we need to factor the expression 4 tan squared of theta plus tan theta minus 3. That was 4 tan, not 4 chan. Nobody go on 4 chan, we're talking about math. I think I'm funny. Ha ha ha. Okay. So, for this problem, we're going to have to get a little creative. We're going to have to use our imagination a bit. We're going to have to look at this and say, you know, if I tilt my head sideways and squint my eyes, not only do I look crazy right now, but this kind of looks a little bit like a polynomial, almost. If we were to say, stick with me here, if we were to say, let u be tangent theta. Just for right now. It's going to be a placeholder. Then we could rewrite all of this as 4u squared plus u minus 3. That is a polynomial. It's definitely a polynomial, right? We know how to factor those. When we do factor it, we're going to find that this breaks up to be 4u minus 3 u plus 1. So if we put our tangent back in, we're going to find that all of this is equal to 4 tangent theta minus 3, that quantity times tangent theta plus 1. And that's it. There's nothing more to this. We are done. All right, cool. Let's look at another example like this. So you're probably looking at this expression thinking like I do. There is no way to factor this. Like, I don't see one right away. What I do see, though, is a way of rewriting cosecant squared in terms of cotangent. And the way to do that is to say, all right, we know that cosecant squared of theta is equal to cotangent squared of theta plus 1. So if I sneak that in for my cosecant x, for my cosecant squared of x, if I sneak this inside of that, what we're going to end up with is cotangent squared of x plus 1 minus cotangent of x minus 3. Well, we can drop the parentheses. When we do, we find that this is equal to cotangent squared of x minus cotangent x minus 2. Now you might be asking what happened to the 1. When we dropped the parentheses, all I did was add the 1 to the 3, which changed it to negative 2. Now from here, we can use that substitution, that idea of the substitution that we used in the last example, and say, all right, let u be equal to cotangent of x. Well, if that's the substitution we use, we're going to find that this entire expression becomes u squared minus u minus 2. Which we can break up as the quantity u minus 2 times the quantity u plus 1. Substituting our cotangent of x back in for u, we're going to find that all of this is equal to cotangent of x minus 2 the quantity times cotangent of x plus 1. And that's all there is to it. Finding out how to rewrite this in terms of cotangent, simplifying that expression, then applying a substitution to help us see how to break it up, and then substituting cotangent back in for u. That's it. Let's move on to another example. So for this problem, we just want to simplify it, right? And one of the easiest things we can do right away is to rewrite cotangent in terms of sine and cosine, which would look something like this. We know we have sine theta plus cosine theta. Those two aren't going to change. But now we're going to change cotangent theta. And cotangent of theta is equal to cosine of theta divided by sine of theta. So how are we going to solve this? What are we going to do here? Well, we can go ahead and multiply this cosine with that cosine. Let's do that really quick. We're going to end up then with sine theta plus cosine squared of theta over sine theta Well, looking at this, I can multiply this sine theta by 1, right? Doesn't change anything. And when I do that, I could represent that 1 with sine theta over sine theta, right? So what I'm saying is, we can rewrite 1 as sine theta over sine theta. So we're going to sneak a 1 in here. 1 times sine theta is still sine theta. And then we're going to rewrite it as sine theta over sine theta times sine theta plus, oh thank God, something that's not sine theta, cosine squared theta over sine theta. Well, now I can multiply this sine theta and that sine theta, that top one. When we do, we're going to get sine squared theta over sine theta plus cosine squared theta over sine theta and I can just bring these all into one fraction, right? Since they have the same denominator, I can just rewrite this as sine squared theta plus cosine squared theta all over sine theta. Well, these turn into 1, right? That's an identity. That's a Pythagorean identity. So when we use that, we get this is equal to 1 over sine theta, which is equal to 1 over cosecant theta, cosecant. My mistake. It is equal to cosecant theta. So all of this math just to show sine theta plus cosine theta times cotangent theta is equal to cosecant theta. That's it. So I've got one last example for y'all. Let's look at it. So to get this problem started, we need to use a trick, and it might not be obvious right away what that trick is. That trick is going to be to turn our denominator into something with an identity. To me, the most obvious way of addressing this particular problem is to multiply our fraction by 1. But we gotta choose our 1 carefully. Let's use 1 minus sine theta, or sine t I mean, divided by 1 minus sine t. Same trick we used last time, but notice I chose how to represent my 1 very carefully. I chose 1 minus sine t because what we're going to get is this is equal then to 1 minus sine t over 1 plus sine t times 1 minus sine t which is equal to 1 minus sine t over 1 minus sine squared t and this is one of our Pythagorean identities. One minus sine squared of t is going to be equal to cosine squared of t. So we can rewrite this now as 1 minus sine t over cosine squared t. Well, that doesn't solve our problem yet. We still need to get this so there aren't any fractions left over. So the next thing we're going to want to do is break our fraction up. If we do that, we're going to end up with 1 over cosine squared of theta, of t, minus sine of t over cosine squared of t well, we can break up this fraction a little bit and we can go ahead and rewrite this fraction. What we're going to get is this is secant squared of t minus sine t over cosine t times 1 over cosine t. All I did was break up this cosine squared. And I rewrote this as secant. Now, we've got tangent here and secant here. So we can rewrite this as secant squared of t minus tangent of t times secant of t. Which if we wanted to factor, we could. This would factor as secant of t times the quantity secant of t minus tangent of t. And that's it. That's all I've got for y'all. Yeah. Have a good one, everyone.